right, so here's some electron configuration and periodicity questions. So kind of going into the periodic trends a little bit here. So first question is, what is the ground state configuration for nickel? So we will get right into it. So we have 1s2, 2s2 this is a relatively straightforward one. Then we're going to end up over here at boron, 2p6, then 3s2, 3p6, 4s2, then comes 3d over here. So 3d, and then nickel is right here at position 3d, 1, 2, 3, 4, 5, 6, 7, 8. So 3d8. Now that is the configuration. Another way you can write it, and this is a standardized way, is sometimes, and I've seen it in some textbooks where they write it in terms of energy level order. So the 3s would be all together, and then the 4s would come at the end. Both are still correct, but this is the way you should write it if you're following the periodic table numerical scheme, and that's the way it would work. That's the easiest way to do it. What is the ground state electron configuration for chromium? Now, chromium is located in this 3d4 spot. So this 3d4, and along with MO, another element in the d4 position, and also all of these d9 positions, these are where we have exceptions occur. Now, what would happen is we have the same configuration. I'm not going to rewrite it. I'll just write the abbreviated. So for chromium, if we go one row up, we have argon. And then the electron configuration after argon is 4s2. And then it would be 3d4 if we were to write it conventionally. Now, because chromium's molecular orbital diagram looks like this in the D shell, looks like this, and the s orbital looks like this, it is not as energetically stable as it could be. When it could become more energetically stable when its d orbitals are filled up either half or all of the way. Now, we have one box that's not open, or that's not occupied by any electron. This is not energetically stable or energetically favorable compared to doing the following, of taking one electron from S and moving it over there. And that will give you the S and the D being completely half filled, which actually is more energetically favorable than having one filled and then an empty spot on the D shell. So this is why this transition occurs for energetic favorability. And our final answer would be in the abbreviated form, argon 4s1, 3d5. And a very similar thing happens with copper, silver, and gold, where you have, instead of 3d9 for copper, it would be 4s1, 3d10. It would fill up the D shell all the way. So now moving on. So write the electron configuration of the copper atom and the copper 2+ cation. So this goes right into what we were saying with the exception. Now, copper is located right here in 3d9. So we can write the configuration as argon, as the abbreviated. So we go to the row above it, look at the noble gas, which is argon, write that in brackets, and then continue. So we're going to have 4s2 and then 3d9. But we just mentioned how the 4s gives an electron to the 3d to fill up its molecular orbitals completely, which is more favorable than having one open slot, just 9 out of the 10 electrons. So it would actually look like this. And this would make copper only have one valence electron. So our valence electron configuration here is just 4s1. These 3ds are not valence electrons. They are not at the highest energy level, principally, which is the 4th energy level. So this is the ground state configuration. Now we need to write the 2+ copper cation configuration. So that's very similar. What we would do is simply take away 2 electrons, and you would take away the highest energy electrons first. So we would take away this 4s, and we would take away 1 from the 3d because that is our new highest energy level after 4s is completely exhausted. So our complete copper 2+ cation would be argon 3d9 as the configuration. And it can't get an electron from another shell because the 4s shell is already completely depleted. All right, let's do another one. So in the reaction of iron and chlorine, what mass of iron is needed to prepare 17.11 grams of iron chloride if, under the conditions of the reaction, the electron configuration of the iron cation is the product of that configuration? So there's a lot going on here. So we have a reaction, but we have some kind of iron chloride. And if you know iron, it could either be a +2 or a +3 cation. The way to figure it out is based on the configuration they gave you. So we know it's a reaction of iron and chlorine. So it would be simply just Fe solid plus chlorine gas, yielding some kind of chloride. So for iron, or some kind of iron chloride. So iron's ground state configuration is 4s2, 3d1, 2, 3, 4, 5, 6. And you notice something here. 4s2, 3d6. What's missing? You have 1s2, 2s2, 2p6, 3s2, 3p6. Normally you'd have 4s come right after, but 4s is completely gone. But 3d6 is what we need. That's where the position of iron is, and that's still there. So this shows us that two electrons were removed from this iron, making it a 2+ cation. So if that's the case, we know our product for this reaction is going to be FeCl2. And in that case, look at that, completely balanced. Great. So this makes our stoichiometry a little bit easier. So what mass of iron is needed to prepare 17.1 grams of the iron chloride? Okay. Now this goes back to stoichiometry, so we'll go through this quickly. 17.1 grams of the iron chloride, which is FeCl2, equals how many moles of FeCl2. For that, we would need the molar mass, which is 55.8 plus 2 times 35.45, which is 126.7 grams per mole, making the number of moles of iron chloride 0.135 moles. Now in this equation, luckily it's very simple, where we have the molar ratios of a 1 to 1 to 1. So if we go from our iron chloride to see how much iron is needed for this reaction to occur, because that's what the question asks for, is what mass of iron is needed, then we can simply just know that 0.135 moles of iron is needed to make 0.135 moles of iron chloride, or iron 2 chloride in this case. So we can simply take our moles, multiply it by 55.8, which is the molar mass of just iron, times 55.8 grams per mole, to come up with 7.54 grams of iron is required for this reaction. So I hope that one makes sense. So now we're going to go on to a couple of the periodic table trends. And the first one is atomic radius. It's very important. All of these have the same concepts involved with effective nuclear charge and the pull of the neutron, not the neutrons, the pull of the protons to the pull of the protons on the electrons in the atom. So let's arrange these atoms from smallest to largest. Beryllium, magnesium, calcium, barium. And you notice they're all here. They're all in 2A. And we know something about the periodic table atomic radius trend is that it increases going down. So increases. And then it decreases going to the right because of effective nuclear charge. And you're adding protons by still having the same energy level. And going down, you're adding principal energy levels. So it's going to be decreasing going to the right. So it would simply just be the smallest would be beryllium. The next largest would be magnesium, then calcium, then barium. So that's actually just the answer. Wow, it's actually written right there. Okay, pretty easy. Next, which of the following elements has the most negative electron affinity? So in other words, which has the strongest affinity to acquire an additional electron? Okay, because we know when you acquire an electron, energy is released. So which one releases the most energy, meaning it's the most favorable to accept an electron? Now, electron affinity is high going to the right, and it decreases going down. And this has to do with the pull of the protons on the electrons. So let's just take a look at our selected atoms. So aluminum, silicon, sulfur, and chlorine. Now, chlorine is a noble gas, not noble gas, no. Chlorine is a halogen. And a halogen has 7 valence electrons. It just requires 1 more. So it has a very strong affinity for the extra electron, very similarly to how ionic bonds work. So we know chlorine is going to have the highest electron affinity. Sulfur is going to have the second highest. Silicon will have the third highest. And aluminum will have the least because aluminum forms a cation. So it wants to lose electrons generally, not gain. So its electron affinity is going to be pretty low. Okay, so now let's arrange more atoms from largest or from smallest to largest, but when we involve charges, in this case, cations. So we have lithium, beryllium, and lithium plus. All right, so let's talk about it in the effective nuclear charge manner. So what happens is, as we go across a periodic row, a period, what happens is the principal energy level stays the same, and you're just adding more electrons to it, right? That doesn't change the size at all because it's the same principal energy level, the same ring, if you will. But you are increasing the number of protons. Since you're increasing the number of protons, those protons have a larger pull on the electrons in that outer ring, therefore making the element smaller or the atom smaller. So if that's the case, then beryllium is going to be smaller than lithium. Now, lithium plus, where is lithium plus when it loses its electron? It loses an electron, so it only has 1 electron in that energy level, so it shrinks because that energy level is no longer occupied by an electron, and now it has the configuration of helium, which is over here. When lithium is charged, it's going to have 1 less energy level than normal lithium, meaning it's going to be smaller than lithium. We know lithium will be the largest. Beryllium will be smaller than lithium because it has 1 more proton to pull in the same number of rings of electrons. And then finally, the lithium plus will be the smallest because it has 1 less energy level than the lithium and the beryllium, and it has the same configuration as helium. So if we look at anions, let's just take a look at this concept again. You have argon, very small. Everything is close together because you have the maximum number of protons in this row. Then you have phosphorus. So phosphorus has less protons, and in this case, you're taking phosphorus and you're giving it more electrons. Okay? It doesn't matter if you're giving it more electrons because the electrons in the same shell, which those are the electrons that are being added to complete the shell, do not have an effect on the size as much as adding a proton. So if you are adding protons, it then makes the effective nuclear charge larger on the outside electrons pushing them or pulling them in. So a phosphorus, even though all 3 of these have the same electron configuration, phosphorus is going to be the largest because it has the lowest amount of protons to pull in those same number of electrons. Chlorine will be the second largest, and then argon will then be the smallest because it has the most protons to produce a larger effective nuclear charge. So this order is backwards from largest to smallest, but you can flip it around. When you have anions, they get bigger generally by a little bit amount, by a small amount, but they do get bigger because you're keeping the same number of protons, but you're adding electrons in the same energy level, whereas the cations, you are removing an energy level completely, making it very small. Okay, let's do the last 2. Arrange the following from smallest to largest ionization energy. Now, ionization energy is the energy required to kick off an electron or to ionize. Now, this usually increases going to the right and increases going up. So we have beryllium, magnesium, and barium again, and calcium. We have all of these again. So beryllium will have the largest ionization energy. So now it increases going up. So beryllium will have the largest, magnesium will have the second largest, calcium will have the second smallest, and then barium will have the smallest. And this is because of the effective nuclear charge again, and where those electrons that are being kicked off are positioned. In something like barium has a lot of electron shells. The electrons that are being kicked off are going to be the valence, which are further away from the nucleus than the valence of magnesium or beryllium. So that's why you decrease in ionization energy as you're going down on the periodic table. And finally, the last one, arrange the elements lithium, carbon, and oxygen in order of increasing second ionization energy. So for this, we need to take a look at the molecular orbital diagram, or we can just look at it as in terms of the periodic table, but the orbital diagram helps as well if you'd like. So lithium, let's talk about second ionization energy. The first ionization energy, going from lithium to the configuration of helium, is fairly easy because lithium wants to get rid of an electron fairly easily. And that works by the trend. The trend has the lowest ionizations on the left and the highest ones on the right. Because when you have a complete shell, it is harder to lose an electron. It takes more energy to kick one off. So once lithium loses that first electron, which is very easy, losing the second one is extremely difficult because now you have a noble gas electron configuration where that helium is very happy. It does not want to lose an electron or gain any electrons. It is very happy. So to remove one would require a lot of energy. So lithium would have the highest second ionization energy. So put lithium on the right. Now carbon, the first ionization energy is bromine. The second one, all the way to beryllium. So that's not too bad. I mean, if you look at it in the orbital diagram, so we'll look at 2s and 2p. Carbon has 2s2 and then 2p2. You lose one, you lose two, not too bad because it wants to lose that second one, not more than the first, but it wants to lose it as well because having one lone electron in a p orbital is not very stable, not ideal. So having just a filled s orbital is a lot more stable than that. So it wouldn't be too detrimental. So we'll probably put this last for now, and we'll see what oxygen does. So oxygen, we'll write down on the bottom right. Oxygen is 2p4. So maybe we have 1, 2, 3, and 4. So losing the first one, not too bad. Losing the second one, it's pretty bad because we have a half-filled shell here. And very similarly, like we saw for the exceptions of electron configuration for copper and chromium, the same thing occurs where it's more stable to have a half-filled shell than to have one box open. So to forcibly remove this electron from the third box in oxygen would make it unstable, and that would not be a favorable process and would require a lot of energy. So, but not as much as lithium, or not as much as a noble gas losing an electron. So oxygen is somewhere in the middle. So the arrangement would be carbon, oxygen, and then lithium would be the highest. If you have any questions, please post in the comments and be sure to like this video and subscribe to the channel. Thank you.